Welcome. Chapter 7, Eigenvalues and Eigenvectors. This is a big thing in linear algebra. Eigenvectors are vectors that are ideal to form a basis. These are the vectors that we would like to pick for our basis, and the eigenvalues are tied to the eigenvectors. So we will see how to find eigenvalues and eigenvectors, and we will find the matrix of the transformation with respect to the eigenbasis. So in section 3.4, we saw that sometimes it's useful to change bases in order for the matrix to be easier to find, and eigenvectors are the best vectors we could pick. Why is that? Well, the definition will give a hint. An eigenvector is a vector such that A times V equals lambda V. So what does that mean geometrically? It means that after the transformation of vector V through matrix A, the output is still in the same direction. It's vector V multiplied by a certain scalar. It might be 2V or 5V or negative 3V. So it means the vector doesn't change direction. And the scalar lambda, this letter here is lambda, is called an eigenvalue. So we start usually by finding the eigenvalue when we solve exercises, and then the eigenvalue allows us to find the eigenvector. The eigenvector is the real goal. So as a note, a matrix may have multiple eigenvalues, and ideally, if we have a square n by n matrix, we find n eigenvectors. The scalar lambda might be 0, but we like eigenvectors 0 are not interesting. We want to find eigenvectors that are spanning a line so that every vector on that line is actually an eigenvector. So a geometric example first. If we have a projection, we imagine that T is the transformation that projects all vectors perpendicular on the line y equals 4x. Then what are our eigenvectors? Again, eigenvectors are vectors that are not changed in direction after the transformation. So firstly, all vectors along the line, if you project them on the line, are just going to remain what they are. So these are eigenvectors, and in fact, because the vectors don't change direction but also don't change their length, the eigenvalue is 1. If you take a vector v along the line and then you project, then AV equals 1v. AV equals v. So these eigenvectors are all vectors of the form 1k times a certain value. 2,8 is of course an eigenvector, 3,12 is an eigenvector, etc. The eigenvalue is 1 because they stay the same length. But also we have all the vectors that are perpendicular to that line. And these vectors don't change direction because they basically vanish. So these are also eigenvectors, and their eigenvalue is 0. A times v for a perpendicular vector equals 0v. So a key theorem here in order to find eigenvectors is that eigenvalues are such that this equation, equality, is true. The determinant of A minus lambda times the identity equals 0. So let's see how this works. If we assume that lambda is an eigenvalue of A, then by definition it means that AV equals lambda V. From here to there, you may want to pick an example, but saying 5 times vector v is actually the same as making a matrix that has 5s along the diagonal and 0s everywhere else, and multiplying by v. It's going to yield the same as 5v. You may want to try with just a 2 by 2 matrix to see that it indeed this is the same as that. Now if we group these two on the same side and factorize, we get A minus lambda identity times V equals 0, and we assume that v is an eigenvector that is not 0. So if this exists, it means that the kernel is not 0, because v is in the kernel. And therefore, if the kernel is not 0, the matrix here is not invertible, and that means that the determinant is 0. So all these steps can also be worked backwards. This is why I have double arrows every time. Okay, so we are mostly focusing in this section on applying and being able to find eigenvalues and eigenvectors. So how do we do that? We use the theorem above. We want to set determinant equals 0 and find the lambdas that come out. So determinant of A minus lambda identity is this. Lambda identity looks like that. Its lambdas along the diagonal minus 0, and it is this. You can start here right away in exercises. It's always going to be the same. It's the determinant of matrix A with negative lambdas along the diagonal. So 3 minus lambda, 1 minus lambda, and nothing else changes. And we want this determinant to be equal to 0. So let's work through. We find the determinant here, a few steps in order to reach determinant of A equals lambda minus 5 times lambda plus 1. And if this is equal to 0, it means lambda equals negative 1 or lambda equals 5. So we have two eigenvalues, and we now need to find the eigenvectors that correspond to these eigenvalues. So how do we do that? We have two choices. Let's start with lambda equals negative 1. We can either try and figure out what vectors v, or I wrote x here, are such that ax equals lambda x, so negative x in this case, or the other option, which is a little bit smoother, is to use the lambda we found and plug it back in here, or here, let's say. So we want to find this times x equals 0. And that means for the matrix 4, 2, 4, 2 times x equals 0. And just by looking at it, we can see that any vector of the form k times 1, negative 1 is going to fit the bill. So v, or x, 1, negative 1 is an eigenvector, and any multiple of 1, negative 1 is an eigenvector. We then have the second option for lambda. Lambda equals 5, so again 3 minus lambda means 3 minus 5, which explains why there's a negative 2. 1 minus 5 is negative 4. The other values that are not on the diagonal do not change, and we try to find x such that this equals 0. And again, just by looking at it, we can find that x is any vector that is a multiple of 2, 1. So our two eigenvectors are, well, the span of 1, negative 1 and 2, 1. So, but this is basically the basis of all eigenvectors. All right, a second example with a triangular matrix. It's going to make our life easier. When we look for the determinant of A minus lambda I, we still have a triangular matrix, so the determinant of that is just going to be the product of the diagonal entries. So immediately we find that the eigenvalues are going to be 2, 3, and 4. For each of these, we can apply the same strategy as before. We will do, for the first one, lambda equals 2. The diagonal 2, 3, 4 is going to be 2 minus lambda, 3 minus lambda, 4 minus lambda. So it becomes this matrix here. How can we find x such that this matrix times x equals 0? Well, with a little bit of focus and staring, we can find that it's the span of 1, 0, 0. Likewise, for lambda equals 3, how can we make this equal to 0? Well, by taking 3 times the first column plus 1 times the second column plus 0 times the third column, we're always going to get 0. So 3, 1, 0. The last is a little bit more work, but you're also going to be able to find it. You can look at the second row here, and you know you're going to need 4 times this plus 1 times that in order to get 0. And then by reverse engineering, you can find how many of the first column you need. So if we have an n by n matrix and we find exactly n eigenvectors, then we're lucky, it's the best case scenario, and we have a basis, and we call this basis the eigenbasis. If we want to look at the matrix of the linear transformation for this matrix here, the answer is there. Why is the answer falling so quickly? Because this is the exercise we did on the previous page. We had found that lambda was equal to -1 and 5. So what that meant is that if I picked the first eigenvector as my new basis, then its image was going to be -1 times this vector. So that's why it's -1 here. And the image of the second vector in the eigenbasis was going to be transformed to 5 times itself. So this is why we just have -1, 0 and 0, 5. This is going to happen no matter what type of matrix you have. If there's an eigenbasis, then the matrix of the transformation with respect to that eigenbasis is always going to be diagonal, and it's always going to just be the eigenvalues themselves. So that's it for this chapter, an introduction to eigenvalues and eigenvectors. Thank you for listening.